Guys, welcome back. So here we have another question from GATE 2016 on network theory. In the RLC circuit shown in the figure, the input voltage is given by Vi of t is equal to 2 cos 200t plus 4 sin 500t. The output voltage V of t is, and they have given 4 options. So this is the circuit. So if you first take an initial look, you will find like this having like a 2 RLC network kind of thing. But when once you try to solve it, it is going to simplify. So we'll take this circuit. And we also have this Vi of t. So one thing is to notice is that all RLC circuits are linear time invariant systems. So it means that superposition holds. So this Vi of t, I can separate it as Vi1 of t as 2 cos 200t and Vi2 of t as 4 sin 500t, and I'll get my outputs as V01 of t and V02 of t. So my input Vi of t is Vi1 of t plus Vi2 of t. So my output V of t is going to be V01 of t plus V02 of t. Okay, so first let us solve for the case of Vi1. So Vi1 is 2 cos 200t. So omega is equal to 200. So can we find this equivalent impedance? So omega L here, let me call it L1, C1, L2, C2. So omega L1 is 200 into 0.25. So j omega L1 is this one. So it is 25 into 2, so 50j. So similarly 1 by j omega C1 is nothing but 1 by j into 200 into 100 micro. So 100 into 10 power 6. So 4 goes away, 100 remains. So it is 50. 50 by j is minus 50j. So now here only if you notice, these two are in series. So this is 50j, this is minus 50j. So what is their equivalent resistance or impedance? Z equivalent is equal to 0, which means that it is going to be short at this frequency, right? So if it is short, what can you say about V out? If this is some finite impedance, if this is also not short, then Vi of t is equal to V out of t. So can we also see whether this is also some finite impedance and not 0? Okay. So omega L2, j omega L2 is j into 200 into 0.4, which is 80j, right? And 1 by j omega C2 is minus j into 10 power 6 by 200 into 10. So this is 3000. So we'll get minus 500j. So if you see, they are not going to cancel. So this is some finite impedance, and here it is zero impedance. So when there is a zero impedance in parallel with any finite, it is going to be still be effectively zero. So your V01 of t is equal to Vi1 of t, which is equal to 2 cos 200t. So you can go back to the options, and here itself if you try to figure out, only this one is having the same for the 200t case. So this is the answer, but let us also check for this case also. So in this case, if you compare it with input, it is again same, right? So what does it mean? What can you guess for 500t? So we can guess that this impedance is going to be infinite. Only then the same can appear, right? So let us see that. So for the second case, Vi2 of t is 4 sine 500t, and your omega is 500. So your j omega L2 is 500 into j into 500 into 0.4, which is nothing but j800. Sorry, j200, right? And similarly your j omega C2 is, so 10 power 6 by j into 500 into 10. So 5000, and this is 1000 into 10 power 6. So this is also minus j200. So now they are in parallel. So Z equivalent is j200 into minus j200 divided by j200 minus j200. So this is minus j4 into 10 power 4 by 0, which is nothing but infinity. In this case, whatever, minus j infinity or whatever it is. So this is gonna be open. So if this is open and if this is finite, and entire Vi will appear across V out of t. So this anyway we know it will be finite only, because the only resonant frequency was when omega was equal to 200. So you needn't do repeated calculation. Directly you can write V02 of t is nothing but Vi2 of t, which is equal to 4 sine 500. So for this case, you needn't actually write this as j omega L L2, and you no need to get, like, if this is Z1 and Z2, you no need to get the entire expression of Z1 by Z1 plus Z2, then substitute omega. So this is not required here. You just take it, you substitute and see, and one of them is gonna disappear, and here the other is gonna disappear, and you'll get the answer easily. So the answer is option B.